Muscles are essential in the mechanism of all body movements. Muscles attach to bones via tendons which allow bones to move. All skeletal muscle is covered in a fibrous elastic sheath called the epimysium. The epimysium holds the bundles of muscle fascicles together. Each fascicle is covered by a strong sheath of connective tissue called the perimysium. The sarcolemma is a fine tubular sheath which holds the muscle fibers together. Under a high-power EM microscope, it is possible to see that there are smaller myofibrils embedded in the cytoplasmic matrix of each fiber. The cytoplasmic matrix of muscle fibers is called the sarcoplasm. A single muscle fiber is called a myofibril. Each myofibril is covered by a delicate connective tissue called the endomysium. Each myofibril is 1 micrometer in diameter. A myofibril is divided into a light I band and a dark A band. Between the dark band and the light band is a dark line called the Z line. Myofibers contain the contractive tissue which allows muscles to complete their task of movement. This contractive apparatus is called the sarcomere. Smooth and cardiac muscle types are both involuntary and high endurance. Skeletal muscle is voluntary with low endurance. In an isotonic contraction, tension remains the same, while the muscle length changes. Isotonic contraction has 2 elements, concentric contraction and eccentric contraction. In a concentric contraction, the muscle tension increases to meet the resistance, then remains the same as the muscle shortens. In eccentric, the muscle lengthens due to the resistance being greater than the force the muscle is producing. In an isometric contraction, the muscle tension changes, but the muscle length remains the same. Tension builds, but muscle neither shortens or lengthens, and maintains posture. The 2 main proteins involved in muscular contraction are myosin and actin. In resting muscle, most of the myosin is in the myosin ADP-PI form, and the myosin binding site on actin is inhibited by troponin and tropomyosin. Actin is uncovered through the binding of calcium to troponin. This calcium is obtained from the action potential stimulus, which takes place when a muscle is stimulated at the neuromuscular junction. The myosin ADP-PI complex binds to actin. This releases PI, producing the parastroke at the crossbridge and a change of conformation of the myosin head. Essentially, this is what allows skeletal muscular movement. Immediately, another ATP molecule replaces ADP in the myosin head, binding to the actomyosin complex to form an AMP-ATP complex. The actin is released. The myosin head reverts to the resting conformation. ATP is hydrolyzed to ADP-PI, the resting state. The I-band is the zone of thin actin filaments. It is not superimposed by thick myosin filaments. The two actin filaments are pulled towards each other towards the myosin in the center. The A-band contains the entire length of a single thick myosin filament. The H-zone is the zone of the thick filaments that is not superimposed by the thin actin filaments. During muscle contraction, the A-band remains the same length. The I-band shortens, the H-zone is reduced. In relaxed muscles, actin and myosin filaments lie side by side. The H-zone and I-bands are at maximum width. In partially contracted muscle, the H-zone and the I-band are reduced and the A-band doesn't change. In fully contracted muscles, the A-band remains the same length. The I-band shortens and the H-zone is disappeared.